This is the section 9.6 notes. In section 9.6, we're going to look at the method of moments. So the method of moments is one of the oldest methods for deriving point estimators. And so just to remember, recall we're going to just review what moments are. So we use mu prime subscript k, which is equal to the expected value of y to the k, and we call that the kth population moment about the origin. Now we could define m prime k to be equal to the average of the yi's to the k, and we could call that the kth sample moment. And so the whole idea here, what we're going to do is we're going to estimate mu prime sub k, which is a parameter, by its corresponding sample moment. And so we're going to look at several examples of this. So suppose that y1 through yn are IID uniform 0 to theta. And so the first thing we're going to do is we're going to estimate theta using the method of moments. So to do this, we're going to start out with the first moment, or the expected value of y. Notice that is equal to mu prime 1, and the expected value of y in this case is mu, which is equal to theta divided by 2 for the uniform on 0 to 1. So theta in this case is equal to 2 times mu prime 1. Notice that comes from right here. So if we let theta hat be equal to 2 mu prime 1, which is equal to 2 times 1 over n, the sum I equals 1 to n yi, or the first sample moment, that is going to be equal to 2 y bar. Alright, so next we're going to show that our estimator is a consistent estimator of theta. So notice here, by the law of large numbers, since the variance of y is finite, and we know that again because this is a uniform distribution, we know that y bar converges in probability to mu, which is equal to theta over 2. We've proved that previously. Also, we know that 2 converges in probability to itself. So therefore, we can use our theorem from earlier on in the notes to say that 2 y bar converges in probability to 2 times theta over 2, which is equal to theta. So 2 y bar is a consistent estimator. Right? Next, we've got a fact to look at. So our fact states the following. Sample moments are consistent estimators of the corresponding population moments. So in other words, you could prove in general to say if we take the kth sample moment, which is equal to the average, or 1 over n times the sum of yi to the k, this is going to converge in probability to the mu prime k, or that population moment about the origin. So usually estimators found using the method of moments estimators are also going to be consistent, but they might not necessarily be the MVUE. So for an example, let's look at a gamma distribution. So we're going to let y1 through yn be IID gamma alpha beta, and the first thing we're going to do is we're going to use the method of moments to estimate both alpha and beta. So first of all, let's define what our first moment is. So mu prime 1 is going to be equal to mu, and for a gamma distribution, that is alpha beta. And we're going to need this later on, so I'm just going to call this 1. Also recall that the variance of y, or sigma squared, for a gamma distribution is alpha beta squared. So if we want to look at the second moment, or mu prime 2 about the origin, that's equal to the expected value of y squared. And we can use the variance to help us get that. And because we know this is equal to the variance plus the expected value of y squared. So therefore, the second moment is equal to alpha beta squared plus alpha beta squared. So the second moment about the origin is equal to alpha beta squared plus alpha beta squared. And we're going to call this 2 because, again, we're going to need that here in a minute. So notice that 1 and 2 are equations and two unknowns. Alpha and beta. So what we can do is we can solve simultaneously for alpha and beta. So first, looking at 1. So notice that 1 becomes alpha, which is equal to mu prime 1 divided by beta. And so we get that by just multiplying both sides by beta. So we're going to substitute this into 2. And this is what we're going to get when we do that. We're going to get that mu prime 2 is equal to mu prime 1 divided by beta, beta squared, plus mu prime 1, beta squared, beta squared. So notice we're going to get some cancellation of our betas here. So we're going to get that mu prime 2 is equal to mu prime 1 beta plus mu prime 1 squared. And if we solve for beta, we find that beta is equal to mu 2 prime minus mu 1 prime squared divided by mu 1 prime. So next, what we can do is we can replace mu prime 1 with the corresponding sample moment. And do the same thing for mu prime 2. And if we do this, we get the following. We're going to find that beta hat is equal to m2 prime minus m1 prime squared divided by m1 prime. Substituting in what those sample moments are, we get 1 over n, the sum, I equals 1 to n, yi squared minus y bar squared divided by y bar. So notice here to get the y bars, we get the y bars because y bar is equal to 1 over n, the sum of the yi's, which is exactly what the first sample moment is. And then further, this is equal to 1 over n times the sum, I equals 1 to n, yi squared minus sum, I equals 1 to n, yi squared divided by n, again, all over y bar, which is equal to the sum, I equals 1 to n, yi minus y bar squared, divided by n y bar, and you can show this is equal to n minus 1 s squared in y bar. So that's what we would use to estimate beta if we're using the method moments. Well, of course, we'd also like to estimate alpha, so I'm going to use my little bit of space that I've got right here to do that. Notice that alpha prime we showed was equal to the first sample moment divided by beta hat. Well, our first sample moment is y bar, so this is going to be y bar divided by, well, our estimate for beta hat that we just had. And this simplifies to n y bar squared divided by n minus 1 s squared. And that is an s right there. And remember, this is for a gamma distribution, so this is showing how you can take the sample mean and the sample variance, and what we can do is we can estimate the different parameters for this gamma distribution. All right, next what we're going to do is we have this claim up at the top of page 20, which says that usually estimators found using the method of moments are consistent. So let's now show that that alpha hat and beta hat that we just found, let's actually show that both of these are consistent estimators of alpha and beta. So we know the following. We know that the first sample moment is consistent for the first population moment. In other words, we know that y bar converges in probability to alpha beta. We also know that the second sample moment converges in probability to the second population moment. Or in other words, if we take the sample second moment, we know that it's going to converge in probability to alpha beta squared plus alpha squared beta squared. And notice both of these values are coming from what we did in part A. So now, let's first look at beta hat. Okay, so here's our beta hat. Well, first, we know that y bar squared converges in probability to alpha beta squared. And so this is going to be by theorem 9.2b. So, beta hat, which is equal to, again, 1 over n, the sum I equals 1 to n, yi squared minus y bar squared divided by y bar, is going to converge in probability to alpha beta squared over alpha beta, which is equal to beta. So beta hat is a consistent estimator of beta. So notice where these are coming from. So if we look at this in 3 separate pieces, we know from up above that this piece converges in probability to this. This piece converges in probability to this, and the y bar converges in probability to alpha beta. Combining all three of those pieces is where this comes from, and the reason we can do that is, again, by that theorem 9.2. So you always want to keep that theorem handy, because when we work with consistency or convergence in probability, it comes in really handy. So also, remember, so we've just shown that beta hat is consistent. We also want to show that alpha hat is consistent, so that's the next thing we need to do. So also, alpha hat is equal to y bar over beta hat. Now notice we've already shown that beta hat converges in probability, and we've already shown that y bar converges in probability, so again we're going to use that theorem 9.2. So since y bar converges in probability to alpha beta, and beta hat converges in probability to beta, again by theorem 9.2, we know that alpha hat, which is equal to y bar divided by theta hat, is going to converge in probability to alpha beta divided by beta, which is equal to alpha. So in other words, what we've shown here is that alpha hat is a consistent estimator of alpha. So anytime you're asked to show if something is consistent, you're going to be working with convergence and probability. And keeping that theorem 9.2 handy is a good way to help you go about that, because if you can show that different pieces converge in probability, then you can use 9.2 to put those pieces together to show the overall piece that you want to show, or overall, convergence and probability that you want to show. We only have one more page in this section. So our last question is are alpha hat and beta hat, are they MVUE? So remember, going back to page 20, we were able to show that these estimators are usually consistent, but not necessarily the MVUE. So let's see what happens for this example. All right, so in order to show MVUE, remember we're going to look at our likelihood function. So our likelihood function here, we've got y1 through yn given alpha beta. We're going to have 1 gamma alpha, beta the alpha to the n, y1 to the alpha minus 1, all the way out to yn to the alpha minus 1, e to the negative 1 over beta, times the sum I equals 1 to n yi. Alright, so now we're going to look at that ratio of the likelihoods. So we've got r is equal to, in the numerator, I'm going to have the likelihood in terms of x. In the denominator, I'm going to have the likelihood in terms of y. Next thing I'm going to do is write that likelihood again in terms of x and y. So in the numerator, so we've got the likelihood written in terms of x. Next, we're going to write the likelihood in terms of y. Okay. Now we're going to see if we can simplify some. Notice that this term and this term are going to cancel. So that's going to leave me with the following. And we can simplify this further. Notice this is going to be equal to the product of I equals 1 to n xi divided by the product I equals 1 to n yi, all to the alpha minus 1, e to negative 1 over beta, times the sum I equals 1 to n xi minus the sum I equals 1 to n yi. Remember, our goal is we're trying to figure out when this is going to be free of alpha and when it is going to be free of beta. So notice that R, or our ratio here, is free of alpha and beta if and only if the product from I equals 1 to n xi divided by the product I equals 1 to n yi is equal to 1, and we also need that the sum from I equals 1 to n xi minus the sum I equals 1 to n yi is equal to 0. The reason for this is if these two, or if this one minus this one is 0, this piece is going to become 1. And then if this ratio is equal to 1, then we're going to have 1 to some power, so this just becomes 1. So that's how we can get rid of alpha and beta. So this is the same as saying that R is free of alpha and beta if and only if the product I equals 1 to n xi is equal to the product I equals 1 to n yi, and the sum I equals 1 to n xi is equal to the sum I equals 1 to n yi. Alright, so now we can apply the Lehmann-Scheffé theorem. So by Lehmann-Scheffé, or Lehmann-Scheffé technique, I should say, the product I equals 1 to n yi and the sum I equals 1 to n yi are MSS for alpha and beta. Now, since alpha hat and beta hat are functions of the sum I equals 1 to n yi and the sum I equals 1 to n yi squared, and notice this is not MSS. Alpha hat and beta hat are not MVUE. And it ends up that the MVUE in this case are difficult to find. So this is going to conclude the Chapter 9.6 video.